Hi folks, I'm going to talk about generative adversarial networks today, also known as GANs. GAN was invented by Jan J. Goodfellow. GAN is an exciting and innovative idea in all of deep learning today. GAN, simply speaking, it generates images that look very real, yet those images are not real, but rather fake. The idea or the concept of GAN is so important that Jan Layman, who won the Turing Prize, which is equivalent to Nobel Prize in computer science last year, he said that is the coolest idea in deep learning in the last 20 years. Before we delve deeper into GANs, let me talk about the things that you may want to make sure that you have some idea about, which are prerequisites. For understanding GAN, you kind of need to know neural nets, backpropagation, CNN, which is convolutional neural nets. You may need to know calculus a little bit, particularly derivatives and partial derivatives and exponential and logarithmic functions. Basic knowledge of probability distribution, density functions. These are pretty good. But in addition, if you happen to know RNN, that's good. But if you really know probabilistic measure theory, topological manifolds, that's excellent. You know all the math that you need to know in order to understand the theory that goes behind GANs. Now let me talk about learning objectives. What are we going to learn here today? We are going to learn what GANs are and how it fits under the generative models. Structure of GAN models we are going to talk about. We are going to talk about implementation outline of GAN model and different types of GAN models and learning outcome measurements. Now let me show you some images that were actually created by GANs. Here are some images. You can see how realistic looking these images are. They look like real person's images, yet those are not real. Those are fake. Here are some potentially exciting applications of GANs. GAN, as I mentioned earlier, for our purpose, we are restricting it to image generation, even though GAN could be applied to other things such as audio. GAN generates images that look like real-world images, and we could use those images as training examples for our algorithm. Self-driving car is one example where a self-driving car could face a lot of scenarios in the real world which cannot be predicted. We could use GAN to generate images or scenarios. Those are not exactly collected from the real world, but generated by GAN algorithm. We could use those generated images as our training data to train the self-driving car algorithm, and it will learn even though the car never actually experienced it in the real world. So in theory, we could have a self-driving car in the garage that knows a lot about the real world scenarios even though it never did drive a single mile on the road. Another example could be robotics. In the field of robotics, you could have robots, those are trained on artificially generated data, and it could know a lot about a warehouse even before it steps into a warehouse. Other examples could be character generation in video game, and then fashion industry is another example. And medical imaging is one example where we could use GAN because of the privacy issues. You do not have access to a lot of medical data, so we could use GAN to generate data to train our models. Another example could be in reinforcement learning. We could generate time series data that could be used in simulation in reinforcement learning. So that's another example of GAN generated data. These are some exciting fields where GAN could be used. So there is reason to learn about GAN and understand different algorithms. Now let me talk about how GAN fits under the generative models. Let me talk about generative models. For the sake of our purpose, we can think of generative models as something that generates images. Okay? So it creates data of images. Now, the way generative models create images is done mostly in two different ways. One is through estimating the probability density function, PDF. Okay, under this category, you have variational autoencoders, pixel CNN, pixel RNN. The other model or other group is that does not use the probability density function, and under that category, GAN is the most prominent one. Actually, what GAN uses is something different. It uses game theory. It uses something called Nash equilibrium, which we will talk about in one of the next slides. Please do keep in mind that GAN is just one example of generative models, okay? And it happens to be a very useful one. That's the important part. Now let me give you a layman's view of GAN architecture, or an ordinary person's view of GAN architecture. The principle that goes behind the GAN architecture could be expressed in multiple ways. I'll try to explain it by giving different examples. Think of a scenario where a person makes fake dollar bills and tries to pass that dollar bill to the banker. Now, the banker is always trying to catch people who are making fake dollar bills, whereas the person who is making fake dollar bill is trying to deceive the banker. So there is a conflicting interest here. One is trying to deceive the other. So the fake dollar bill person is trying to, or she is trying to deceive the banker, and banker is trying to catch the person who is making fake dollar bills. Another example would be cat and mouse game. Okay, one is trying to deceive the other. Another example would be art expert. Okay, an art expert and somebody who makes fake art. The person who makes fake art is trying to deceive the art expert. Art expert gives a rating or some sort of confidence level in whether it is a genuine piece of art or a fake one. And another example would be bouncer and a drunk guy who is trying to get into the bar. All these examples actually fall under one category, which is the Nash equilibrium. Let me go ahead and talk about Nash equilibrium a little bit so that you get a better understanding of the principle that goes behind the generative adversarial networks, or GANs. The way Nash equilibrium works is this. Think of a game, any scenario where two players are involved. They will settle down at a position where it's beneficial for both of them, which we call the equilibrium point. That means the point where they settle down is beneficial for both parties. If one of them kind of goes away from that point or moved from that point, the other person is gonna make similar or opposing move depending on what goes in or her benefits. So what's gonna happen if one of the persons make a move is gonna be resulting in another person making similar move. As a result, both parties end up losing. That's what it is. So Nash equilibrium is a point where both gamers are gonna stay because it's the optimal position for both of them to be in. It's beneficial for both of them to be in this position. And Nash equilibrium has a lot of application, by the way. It has application in economics, game theory, computer science, sports. It's a very useful concept. By the way, for this principle, Mr. Nash was awarded Nobel Prize as well. I think it was for economics. Here is another way to look at GAN from a layman's perspective. So you have a generator that generates data, right? And then you can see initially it generates something silly, right? Over time it gets better, right? It creates a dollar bill which looks very close to real dollar bill. In the initial case, what happens, the generator generates something which looks silly and the discriminator says that it's fake, right? Second one is fake too. The third one, it gets better to the point that the discriminator cannot distinguish between the two. So this is a cat and mouse game, or drunk guy and bouncer game. So this is what it is. So this is something that helps you see how GAN structure works. And of course, this is for somebody who is like an ordinary person or a layman. So that's how you'd look at the principle that goes behind GAN architecture. Now I'm gonna look at GAN structure or GAN architecture from a computer scientist's perspective. A computer scientist would look at GAN slightly differently. He or she is gonna look at something called generator and discriminator. The job or task of generator is to generate fake data, which is here. And the task of discriminator is to create classification, either it's real or fake. And the discriminator, by the way, is receiving both fake data and the real data. That means in terms of dollar bills, it's receiving data for fake dollar bill, and it's also receiving data for real dollar bill. That means images of both real and fake dollar bills. Then it's going to classify it either as real or fake. Now let's look at it slightly differently. So in terms of training, so what's going to happen, you have two things. One is discriminator, one is generator. So generator and discriminator. So what you do is you give the data, and the discriminator receives that data, it discriminates, or it kind of classifies rather. So you have two loss functions. One is discriminator loss and one is generator loss. So let's hold the generator loss fixed, okay? So keep it fixed, okay? And then train the discriminator. So what you're going to do, you're going to take in the data and create the discriminator loss, and through back propagation, you're going to update the discriminator parameters or weights. Now let's do the same thing for generator loss. Now in this case, you hold the discriminator loss at a constant and then train the generator. Now here is a little bit of catch here. You of course use the back propagation. Look, the discriminator loss is connected to the discriminator directly. However, the generator loss is not directly connected to the generator. It has to back propagate through the discriminator into the generator. So that makes the training of generator a little bit more challenging. There is a little bit more involved, and you have to be careful in what loss function you are using. So when we are talking about loss function, we have to be careful, because this is not like the regular loss function that you are used to in neural nets. This loss function is slightly different. It actually has two different components. One is the discriminator loss, another is the generator loss. Somehow you have to combine these two loss functions in a way so that you can create an optimal loss function. This actually involves some sort of combination of two distributions, okay? Ideally, we'd like to see the difference between two distributions, because you are trying to make sure that you are transforming one distribution to another. So the loss function should involve some sort of combination or difference between two distributions. Here, when I talk about two distributions, make sure that I clarify it. The first distribution is the distribution of the samples, the original distribution from which the samples are coming. The other distribution I'm talking about is the distribution of this fake data generated by the generator, which takes as input, by the way, some random data points. So the loss function for GANs, I did not really want to introduce any mathematics, but this is the least I could. These loss functions are very simple and very sophisticated, so I thought I would mention about them. Remember, I talked about two distributions that we are dealing with here. The first one was actually initially proposed by Mr. Goodfellow. This is called minimax loss. What it is, d of x is the output or outcome of the discriminator. So here there are two components, two expected values. You can see here there are two expected values taken here. In the first case, what's happening, the discriminator is trying to maximize this value, expected value of log of d of x. On the other hand, the generator is trying to minimize this guy, finding the expected value of log of 1 minus the d of g of z. Remember, g of z is the output of the generator that goes into the discriminator. So what you want to keep in mind here is this. These are two conflicting or adversarial objectives. Discriminator is trying to maximize this, and this function has no influence, or this expected value has no influence on the generator. And on the other hand, generator is trying to minimize this thing. Okay? Now, this minimax algorithm, or minimax loss rather, has some issues in terms of training. Those issues are actually addressed by WGAN or Wasserstein GAN that uses EM distance or earth movers distance. This is, by the way, it could be explained in a very simple way, yet this is very advanced mathematical concepts, probability theory. What it involves is this: you are transforming one distribution into another. It's a distance metric that you are defining. The Westerstern GAN, it has advantage over this one, over the other one, Minimax, is that it addresses some of the training issues that we run into when we are training GANs. One is vanishing gradient, another is mode collapsing, another is convergence. So these things are well addressed by this algorithm or this loss function. Now, I kind of would like to give you a little bit of idea on how this works. It's kind of like simple and yet very nice. Think of a mountain right in front of you, okay? You have a mountain, it has a certain shape. You can think of it as your probability distribution. Now, you want to transform this mountain into a different mountain, that means into a different probability distribution. What you do, you take earth or dirt from this mountain and move it to the other. That means you create a new shape by moving or adjusting the earth from the first mountain. That's where the name earth mover's distance comes from. And this is very simple, very nice and very useful loss function. As you can see, it is just d of x minus d of g of x. So this is the real input that's going into the discriminator, and this is the fake input or output of the generator that goes into the discriminator, and you take the difference. And this is very simple and very powerful, again, just to mention. Now let me talk about how the actual GAN training process works. So your generator is going to take in two sets of inputs, two mini batches, okay? So it's going to take a mini batch of real samples, and it's going to take a mini batch of fake samples. That's output of the generator. These two groups go into the discriminator, and then discriminator uses classification to address that, basically figure out which one is real versus which one is not real. Now do keep in mind, generator taking in as an input some random value, okay, and trying to give you an output that's going to mimic the real images. Now let me talk about some of the challenges that we face when training GAN. Remember, GAN loss function, it has two components. They are competing against each other, adversarial to each other. That's where the word adversarial comes from, generative adversarial networks or GANs. So calibration is a problem for this type of loss functions. Then there is something called weak discriminator. In this case, the discriminator is too easy to be fooled. What happens, generator creates anything and passes it through the discriminator, and discriminator says it's good. So what happens in reality, generator takes in garbage and gives out garbage. So garbage in, garbage out. So it gives some really bad output, and yet it passes. So that's the problem. Then the other problem, by the way, this problem I kind of look at it as a bias problem, okay, bias. And this one, on the other case, which is a variance problem, strong discriminator. What happens is that this discriminator is too strong. It can classify everything very properly. As a result, what happens is that discriminator does not give enough feedback to the generator. So the generator does not learn. What happens, through back propagation, discriminator is sending gradients that are smaller, smaller, and smaller. As a result, you have a problem with vanishing gradient. So this is the kind of like variance problem. I kind of think of it that way. And then there is something called mode collapsing. That's an interesting situation where your discriminator gets stuck in a local minimum or local extreme value, right? In this case, it is minimum. So what ends up happening is that it misses the global extreme value or global minimum. So it is easy to fool the discriminator with just a limited number of data points, limited number of fake data or fake images. It could be as little as one, okay, as few as one data point or one image, or it could be just a few images. So what ends up happening is that generator ends up generating only a few different images or just one image and passing it through the discriminator. This problem could be addressed and solved using, by the way, WGAN or Wasserstein GAN, as well as another. Now let me talk about a little bit of pseudocode for GAN architecture. This is something that was presented by Mr. Goodfellow in his original paper that was published in 2014, original GAN publication. So basically what you are doing is this, you are sending in mini batches here, okay, mini batches of real and fake data. Then you are holding generator constant and you are training the discriminator, okay, and you're updating it through backpropagation. Once you're done with this, then you go ahead and update the generator through backpropagation. So you're using backpropagation to train both parts of this algorithm. This is the minimax algorithm, remember? This is the minimax algorithm. So you are trying to train it by holding one constant, and in the second case, please note that you are just training the generator. Here are some applications of GAN. So this is image to image translation. This is the input that's going in. This is the ground truth, which means the actual image, and this is the output of the GAN model, image to image translation. As you can see, these two are very close to each other except for the colors. Next is conditional GAN. You can think of it as this. If you are generating handwritten digits using MNIST, you could generate any one of the 10 digits. There's general GAN, which is like joint probability of X and Y. But in conditional GAN, what you're doing, you're finding the probability of X given Y. What it means is that, to put it in a simple term, this is what it means. You are just generating, let's say, one digit, let's say 9. Okay? So that's what it is. In conditional GAN, you are generating one specific outcome, as opposed to general GAN, where you could be generating anything from the sample space or the probability distribution. Here is another example. It's called progressive GAN, where both generator and the discriminator, they kind of progressively increase the layer, basically in size, 4x4, 8x8, 16x16, and what it does, the impact of it is it trains faster, and it also gives you better quality images, as you can see right here. These images are quite good. Here is cycle GAN. What cycle GAN does is this: it transforms from one space to another, like from apples to oranges. That's what it is. So it maps the function. So generator maps from X to Y, right? This is a function. So this is a function, and your objective is to make sure that g of X is as close to Y as possible. And they also go over the inverse function to make sure that, so here is the inverse function to make sure that the input that you are generating, or the image that you are generating, that's close to the reality. Here is another one, super resolution GAN or SRGAN, right? It takes low resolution images and converts it into high resolution images. So this is the ground truth, the original, and this is what generated by SRGAN. As you can see, it's quite good, very close to the real image. This is very exciting. Here is another one, image in painting. So this is the real picture. So in image in painting, what do? You block out a certain portion. Okay, you blacked out here this square shape. Now you try to regenerate this thing. So through using image in paint, this is what you get, the regenerated car. Now this is what you get by using another algorithm, which is called CE context encoder. You can do a side-by-side comparison to see how effective GAN is in regenerating images from missing data. This example is an exciting one. It's one of my favorites as well. Text to speech. Imagine a scenario, a world where all the textbooks, or all the books, not textbooks, just any books or any material on the internet could be read, and it could be read in such a way so that it sounds like as if a natural person is reading it. That would be a wonderful thing. And yes, GAN could be used to synthesize text to speech so that it sounds more natural. It sounds like as if a real person is reading the text. This is also another neat one from text to image, but unfortunately the image didn't come out quite good when I uploaded it. So the text is basically saying, oh, it's a bird, red and gray bird with thick beak or something. And it ends up creating something like this, which is pretty good, I think. So this is actually, if it were to be placed properly, you'd have seen this is a really nice picture of a bird. Here are some applications of GANs which are not exactly most ideal. It could be used very negatively. So you could generate fake news with GAN. That's a bad example, a bad usage of good technology. And another could be superpositioning images of people without their consent. What it is, basically deep fake. You probably have heard recently how videos are being created for famous people, and those videos they are saying things they probably wouldn't have said in a public speech and whatnot, and things that they wouldn't have they would have appreciated. So it's important not to create things that other people would not appreciate. So deepfake is one thing that Facebook is currently struggling with, how to manage that. There are many scenarios, there are many potential negative use cases of deepfake which uses GAN behind the scenes. So it's important for us to not only know about the technology but also be aware of the bad use cases or negative use cases of the technology. Now let me go through the learning outcomes. So here are some questions for you to answer. So which principle does GAN or generative adversarial networks use? Cat and mouse it uses. Art critic and fake creator it uses. Nash equilibrium it uses. However, it doesn't use what? Superposition principle. Does GAN use any kind of probability density function? The answer is no, it doesn't, so it's false. So is backpropagation different for GAN compared to neural net? The answer is yes, because look here, GAN has multiple adversary components with opposing interests, okay? In a typical neural network, it doesn't happen. You have just one loss function. In GAN, we have one loss function. However, it has two different competing loss functions built inside of it. Now, how do you update GANs during training? Basically, you have discriminator loss and generator loss, so you update them sequentially, okay, by holding one constant while updating the other. So when you're training for the discriminator, you hold the generator constant and vice versa. What are some of the challenges of training GANs? By the way, all of these four are the challenges of training GAN. So generator giving out inconsistent output, mode collapsing where it creates only a few examples regardless of the input variable, regardless of what random value you put in as input to the GAN, input to the generator, then vanishing gradient problem, and also does not converge. All of these are issues that we need to deal with when we are dealing with GAN training. However, please do keep in mind that all of these situations could be addressed by WGAN for the most part, not 100%. Wasserstein GAN, this is very useful. WGAN or Wasserstein GAN is very practical, and many of these, or almost all of these issues are being addressed by WGAN. Now, the last thing here is this. All of this theory and everything is great, wonderful, excellent. However, true learning happens when you actually sit down and do the work in an actual project. So my recommendation would be that you use the MNIST dataset, okay, and use GAN to generate. Use the GAN algorithm and the MNIST dataset to generate handwritten digits, images of handwritten digits. If you go through the steps of GAN architecture and try to implement it, that would be a wonderful experience. It would truly give you an understanding, a solid understanding of the topics that I discussed tonight, or today rather. Let's revisit our objectives. So we have had 5 objectives, and did we cover all of them? The answer is yes. We talked about what GAN is and how it fits under the generative models. We talked about the structure of GAN models. We talked about implementation of GAN models, and we gave you a pseudocode on how to implement it, and different GAN models, examples of different GAN models. We have shown it. We have talked about learning outcome measurements. Basically, we went over the questions that you need to answer. So yes, we did cover all of it. Finally, a big thank you for your time, and if you have any questions, please feel free to ask me. Thank you and have a wonderful day.